In this confidence interval video, we will derive the confidence interval formula. We will walk through a simulation of confidence intervals calculated with samples polled from a known population, and we will walk through a calculation of a one-sample confidence interval with the t-distribution. Please come along, join in, it'll be fun. X-bar, the mean of a sample, is an estimator of mu, the population mean. However, we know that if we sample and calculate one sample mean, x bar, that this value is likely to be either larger or smaller than the true population mean. We could repeat this process again and again, and x bar would change, even with the same sample size. X bar is a random variable that is normally distributed with a mean of mu and a standard deviation of sigma over square root of n. We know this from the central limit theorem. Mu, though, is not a random variable. It has a fixed but unknown value. So let's think about the sampling distribution of the sample means and what that can tell us about confidence intervals. So again, x bar is a random variable that is normally distributed with a mean of mu and a standard deviation of sigma over square root of n. We could standardize this to a normally distributed z, which is x bar minus mu over sigma over square root of n. And we know, for example, that the area under a normal curve between negative 1.96 and positive 1.96 equals 0.95. And we could generalize this to, excuse me, to z greater than negative z at alpha divided by 2 and less than z alpha divided by 2 equals 1 minus alpha. So at the 95 percentile that we looked at on the left side, we have alpha equals 0.05, and then alpha divided by 2 is 0.025. So z at 0.025 and z at negative 0.025. We could then, because we know that z equals x bar minus mu over sigma over square root of n, substitute that back in for z. We could use a little algebra and set mu in the middle because that's what we want the confidence interval for, and rearrange the terms algebraically. And then once we rearrange the terms, we know that the lower limit of the confidence interval equals x bar minus z sub alpha divided by 2 times sigma over square root of n. And the upper limit equals x bar plus z sub alpha divided by 2 times sigma over square root of n. Again, remember that x bar is a random variable, the sample mean, and mu is a fixed but unknown value. So we can construct confidence intervals in a general sense, that is the estimate plus or minus the margin of error. In our case, when we're interested in a confidence interval for the population mean, the estimate is the x bar, and the margin of error equals the confidence multiplier times the standard error. Right, so the confidence multiplier will either be a z or t multiplier, depending on if we know the population standard deviation, times the standard error. If the population standard deviation is unknown and we're approximating it with the s, or the standard deviation of the sample, the standard error is s divided by square root of n. The level of confidence we are striving for determines the multiplier. The variability in the sample data is reflected in the sample standard deviation, and the sample size is n. So again, in general form, we have the estimate plus or minus the margin of error. The margin of error equals the multiplier times the standard error, and the confidence interval equals the estimate plus or minus the multiplier times the standard error. So let's look at a simulation. Here we have a population, n equals 1,000, a non-normally distributed population. And we're going to pull random samples from this population and calculate 95% confidence intervals and 68% confidence intervals. So I did that through a script. This is actually written in Stata. On the left we have the 95% confidence intervals. Those are the bands. And the green points or dots, those are the sample means. So we have 100 confidence intervals with that were generated from samples of sample size 60. And so at 95% confident, we would expect that 95 of those confidence intervals pulled from the population would include the true population mean. The true population mean is 2.2, reflected as the red horizontal line, and the confidence intervals that do not include the population mean in the interval are highlighted in red. And as you can see, there are 5 on the left that do not. So this meets our expectations, right? We have pulled 100 random samples, sample size 60, calculated the mean, calculated the confidence intervals, plotted them, and we see that 95% of them cover the true population mean. Again, x bar is our random variable, and mu, the population mean, is in this case is known. Typically it's unknown, but is a fixed value. So now let's look at the figure on the right. And what did I change here? I changed the confidence level, or the multiplier. So now we're looking at 68% confidence intervals. So what's different between the right and the left? One, there are a lot more excuse me, there are a lot more red intervals that do not include the population mean. Right? We would expect 32 to not be included. And you'll also notice that the length or the width of the confidence intervals are shorter, as one would expect, because the multiplier is going to be smaller. So the width of the confidence interval depends on two quantities, the multiplier and the standard error. More confidence requires a larger multiplier and therefore a wider confidence interval. A smaller standard error implies a more narrow confidence interval. Standard error decreases as n, or sample size, increases. Therefore, increasing n decreases the width of confidence intervals, all else constant. And with the t-distribution, an increasing n increases degrees of freedom, decreasing the multiplier. Again, we use the t-distribution when we do not know the standard deviation of the population, and we use S, or the standard deviation of the sample. So let's work through a problem. We have randomly sampled 30 blue crabs from the Chesapeake Bay and weighed each crab. Pretty small sample. We should be using the t-distribution because we do not know the standard deviation of the population. We're going to use the standard deviation of the sample, which we have measured to be 20 grams, or calculated to be 20 grams, with an average crab weight, or x bar, of 150.3 grams. So go ahead and calculate the 95% confidence interval using a t multiplier. Again, we do this because 1, we do not know the standard deviation of the population, and 2, our sample size is quite small. So please pause the video and calculate the confidence intervals of the weight of the crabs of a one sample mean. We now have our confidence interval, our 95th% confidence interval, and now we need to interpret it in the context of the problem. So what I want you to do is think about A, B, and C and decide which is the correct interpretation. A, there is a 95% chance that the sample mean of crab weights falls in the interval 142.8 grams to 157.8 grams. B, we are 95% confident that the interval 142.8 grams to 157.8 grams includes the true population mean of crab weights in the Chesapeake Bay. Or C, 95% of crab weights in the sample fall in the interval 142.8 grams to 157.8 grams. So think about that. And the correct answer is B, or the correct interpretation. All right, we are 95% confident that the interval 142.8 grams to 157.8 grams includes the true population mean of crab weights in the Chesapeake Bay. Remember that the true population mean is typically unknown, but is a fixed value, and the random variable is the sample mean, or X bar. And so it's the intervals that will vary, and we're 95% confident that this interval will include the true population mean. So thank you very much for joining in the confidence interval video. This video covered kind of the derivation of confidence interval and an example of a one sample confidence interval using a t-distribution. Thank you very much and have a good day. Again, this is Elizabeth A. Albright of the Nicholas School of the Environment.